right, I want to take a few moments to talk about section 2.1 using an example where our data, z, are normally distributed. Okay, so in this scenario where you have normally distributed data, this is our familiar multiple linear regression type example, okay? But a bunch of new notation is going on in this paper. So I want to talk that through and make a little more sense of what's going on here. Now, just as a quick reminder, we are reading through Nelder and Wedderburn's Generalized Linear Models paper. The link to this paper and the complete playlist that I'm making for this paper are in the description of this video, okay? So let's start with, suppose our data Z1, Z2 through Zn are independent with distributions normal with a particular mean that depends on the observation, and then constant variance. All right. So then we have let yk equal this linear combination of x's. Now, this is the way that this paper, Nelder and Wedderburn, this is the way that they lay out how they want to define the distribution of the data, and then this y variable. Then later we have a link function that links the distribution of the data to this y variable. But really, what I want to pause here for a minute, because I want to point out that this is actually saying, as long as we have the appropriate link function, which I'll talk about that in a second. But this is actually exactly the same as our old familiar our old familiar multiple linear regression, where we have z equals x beta plus epsilon. I prefer matrix notation here, so z is an n by 1 vector of outcomes, outcome variables. X is our data matrix, which is n by m. Beta is our parameters, m by 1, and then epsilon is our error terms, which is n by 1. Okay, and in this scenario, we used to say, okay, so each of these error terms are independently, identically distributed as a normal distribution with mu 0 and sigma squared for the variance. Written another way, using matrix notation, you would say, okay, this vector is normally distributed with a mean 0 sigma squared times the identity matrix to show that the off diagonals are all zeros. Okay. All right, and when this error term is normally distributed, then that implies, and x's are, remember, they're fixed. In both these scenarios, we make the assumption that our x's are not random. So therefore, the distribution of z will also be normally distributed, and its mean will just be that x times beta, and then its standard deviation or variance will be sigma squared times that I, the identity matrix. Okay. So this is the old way that we used to write this, and in this old way, we would maybe show our likelihood equation and find the derivative and set it equal to 0, and we would find that beta hat, using maximum likelihood, equals x transpose x inverse times x transpose z. Right? And the reason I'm writing z, you might be used to say, oh, well, why didn't you write y? Well, because remember, I have z here, z equals, right? So it's a little bit different notation, but you can see this is what we're used to. This is the old way of doing things. Okay. All right. So now what's new? What's new is we have this intermediate variable y, and then we have to link these functions together, right, using some sort of link function, or link this information together. All right, so let's talk about that, and then we'll build up to the iterative weighted least squares method that's discussed in section 2.1 of that paper. So let's start with the distribution of z. Okay, so actually let me go back to my paper and let's scroll up. And we see here under section 1.1, the random component, z comes from this density function here. All right, and that's not a normal distribution. but actually it can be. So it's an exponential family of distributions, which in that family, the normal distribution is part of that family. So I just kind of need to rewrite my normal distribution using this notation, and then I'll be able to figure out what alpha is, what G is, what H is, what beta is, and then using that information, I'll be able to figure out what all this other stuff is. Okay? So let's spend some time, let's do that. So F, actually let me change that back to being yellow. The distribution of our data, F of zk, so for particular kth observation, is mu k sigma squared. Sigma squared doesn't need a k because I'm assuming that I have constant variance. All right, so this is the normal distribution. All right, times negative z k minus mu k squared divided by 2 sigma squared. All right. So when I look at that, I don't see exactly what we have here, but I can. All I have to do is kind of rewrite things, and I'll figure it out. So I want to know what theta is. Actually, let me go ahead and write that down. The distribution that we see in that paper, we have z. Now, they don't use the subscript k, but I'm going to for consistency's sake. Okay, so I'm going to add the subscript k. All right, and I'll even add it for phi, because phi technically you could change what phi is for each observation. In this example, I'm not going to because I have constant variance assumption, but you could have it, so that's why I'll go ahead and include k there. And what they've written in the paper is e to the power of alpha of phi k, z k, theta k, minus g of theta k, plus h of z k, close that parenthesis that's attached to, multiplied by that alpha, and then add on a beta of phi k and z k, and then close the parentheses for the exponent. All right, so I have to basically rewrite this, and I want to find, identify alpha, or sorry, theta of k, phi of k, g, alpha, h, and beta. Right? I have to identify basically all these things. All right, so to do that, I just basically need to rewrite this. Okay, just basically use some algebra and rearrange it. First thing I'm going to do is go ahead and pull this into the exponent by taking the log of it. So I'll leave this part alone. Okay. And then I'm going to add the log of that front piece there. So I can see that the exponent of an addition is just multiplication, and then the exponent and the log cancel, and I'm back to where I started. So I haven't done anything, just used a little algebraic manipulation. Okay, and now what I want to do is I want to go and simplify a little bit more. I'm going to square this front piece here. So I have negative zk squared plus, because there's that minus sign out front. So plus 2 zk mu k, okay, and then let's see, minus and then plus, no, minus mu k squared. right? Because minus and a minus makes it plus, but then this minus makes it a negative again. Okay, divided by 2 sigma squared. Okay, for this one, I'm going to go ahead and take out that exponent, just bring it down. Just makes it a little bit easier to write. Okay, so this is basically to the negative 1/2 power, so I just brought it down there. Okay, so my goal is to make this look like this. Notice, key thing here is I have z times my parameter theta, and it's all by itself. Only place I see z multiplied by a parameter is right here. It has that 2 out front, and it has the sigma underneath of it, so I can kind of get rid of those. Okay, what I'll do is I'll factor out the sigma. So I have 1 over sigma squared. And I'll leave the 2 underneath each piece. So I'll have negative z squared divided by 2 plus zk uk minus uk squared divided by 2. All right, and then I still have the, close the parentheses for that, pulling out that 1 over sigma squared. All right, so still trying to make it look like this. I see this piece here. Maybe I should pull that out front. This g of theta, that could be maybe this g of theta could be this piece here. And then h of z could be this piece here. So what am I thinking? I'm thinking that I'm going to go ahead and define theta sub k equal to mu of k, and then phi of k equal to sigma squared. All right, let me go ahead and plug those in first and kind of rearrange some things here. So I have f of zk okay, 1 over phi k squared. All right, zk times theta k. All right, next I want that g, so that I'll have this theta k squared over 2. And then I want that h, which would be plus, let's see, be careful with your signs here. So h needs to be an addition, but there's a negative there, so just put that negative here. Just to remind myself that h is going to have the negative, but g won't. Okay. And then I still have this stuff out back, minus 1/2 log of 2 pi phi squared. Okay. Okay. So now once I'm here, I can identify each piece. So looking up top here, this alpha is going to be this piece. I have z times the theta of k. I have the g, which is right here, and then I have z right here, and then lastly the beta out back. This is the beta. All right, I'm going to go ahead and write that all down. So I have alpha of phi sub k equals 1 over phi sub k squared. And g of theta sub k equals theta sub k squared over 2. And h of z sub k equals negative z sub k squared over 2. And then lastly, we have that beta of phi sub k z sub k equals negative 1/2 log of 2 pi phi squared, phi sub k squared. All right, so now once you have identified what each of those functions are and what theta and phi are, you can go to our back to our paper, and you can figure out what this iterative weight at least squares, what d mu, dy is, etc. Okay, so that's what we want to go ahead and do, and then we want to show that basically that those are going to be equivalent to this equation right here. In order to do that, I do need a link function. Okay, so remember, the link function is what links this y to the distribution of our z's. So our link function. And usually this is written as theta sub k equals f, some function f of y sub k. Right, and in this scenario, remember theta is the same thing as mu. All right, and this beta times x is basically the mean of z. So it makes sense to use the identity link function, which basically just says that theta sub k equals y sub k. So basically just plug this in for the mean, right? And that's what we want to use. We want to use, this is called the identity link function. Okay, and let's see, let's go ahead and scroll back down. So let's go ahead and use that identity link function. Let's remember, so W in the iterative weight at least squares procedure, the weights, let me use the subscript k to note for each weight, we have d mu k divided by, or d mu dy k squared divided by v. All right, and this is what we want to solve. We want to figure out what is this. All right, so let's start with what is mu k. By definition, mu k is the expected value of z sub k, right? If I go to my paper, I can see, let's scroll up. Right here, mu is the expected value of z, which equals the first derivative of g. All right, so this equals the first derivative of g sub k, or g of theta sub k, which will be the derivative of g. So this function, theta sub k squared over 2 d theta. So the derivative of this. Okay, all I've done is I plugged in what is the function of g. All right, what's the derivative of this? Bring down the 2's there, so they cancel each other. So this is theta sub k, right? And it makes sense. Mu equals theta sub k. That makes sense based off of what we just discussed up here, where I'm basically plugging in y using that link function and plugging that in here. All right. So we see that's what mu is. So then if I want to take the derivative of mu sub k with regards to y sub k, right, I'm basically taking the derivative in terms of y of theta sub k. Now remember, what is theta sub k? It's basically, by definition, we're using that identity link function. So theta is y, right? That's the identity link function. So let's plug that in. And what's the derivative of y with regards to y? 1. All right, so I have 1 squared divided by v. What is v? V is the second derivative of theta, of g of theta sub k. Where am I getting that from? Let's go back to our paper, and we see that defined right here. Second derivative of g equals v. Okay, so that's the same thing as the derivative of the first derivative, right? The second derivative is the derivative of the first derivative. The first derivative is theta sub k. So when I take the derivative of theta sub k with regards to theta sub k, what do we get? We get 1. So the variance equals 1. All right, or this V, sorry, not the variance. V equals 1. Okay. Written in terms of variance, remember variance equals V equals alpha of phi times the variance of Z, right? That's another way you could have written V right here, alpha of phi times variance of Z. So remember, V is not variance, really, it's this function right here. You could have written this, and so alpha of phi is 1 over alpha of phi squared, right? And then the variance of Z is phi squared, right? Because Z is normally distributed, and its variance is phi, right? Right here. Right, so again, you would have gotten 1. Right, so V equals 1. So then, plug these in, and what do you get? The weights is 1 divided by 1, which is 1. So our weights are 1. Okay, then we have this other equation that y, so we have a new dependent variable. Here, let me go and pull this up. Where is it? Down here, section 2.1. A modified dependent variable, y equals this stuff. So let's go and write this down. Yk equals capital Yk plus zk minus mu k divided by d mu k dy k. Okay. All right. D mu k dy k, we've already solved that is 1, right? That's right there. So this is basically divided by 1. Let's see, what else do we know? Yk, let me start right here. Mu k is theta sub k, or theta k. Mu k is theta k. So let me go ahead and write that in. Okay, and then it's divided by 1 because I basically have solved these two in the previous. Then if we're using that identity link function, then yk is theta k by the identity link function. All right, so then when you simplify this, right, you divide it by 1 is just itself. These guys cancel, and you're left with yk equals zk. Okay? So basically, the modified dependent variable is actually just the original dependent variable in this scenario with the identity link function and normal distribution. All right? So we have normal weights, our weights are equal to 1, and our modified variable is just the original normally distributed variable. So from there, you can kind of see, okay, well, yeah, this is like exactly the same as the maximum likelihood. All right, but just to kind of bring it all home, the iterative, let me move over here, the iterative weighted least squares maximum likelihood, or at least, the weighted least squares estimator, is equal to x prime, or x transpose, times our a diagonal matrix of weights, okay, inverse times x transpose w times y. All right, this is the weighted least squares estimator, and in this scenario right now, where each of my weights are just 1, then w is going to equal the identity matrix. And then also my y, my modified dependent variable, is just going to equal z. Okay, so this is using matrix notation. So y is a n by 1 vector. Z is an n by 1 vector as well. And this is an n by n identity matrix. All right, so we can see that when we plug those in, we get the weighted least, oops, I don't know why I wrote E there. That should be least squares, so LS. Weighted least squares estimator equals X transpose times I, X inverse, X transpose times I times Z. Okay, so I just plugged in both W and Y, and I get X transpose X, right? The I can basically be dropped because it's just the identity matrix, and I get my weighted least squares estimator here, which I can see that that is equivalent to, let's scroll all the way back up to the top, that is equivalent to the maximum likelihood estimator that you would have in the traditional multiple linear regression scenario where your data is normally distributed. Okay, so we've shown that these are identical to each other.